Well, let's take a look at pressure in fluids and Pascal's principle. So I'm going to try to do the best I possibly can to explain this principle to you. And the principle itself has actually been proven, and we do use it quite a bit, so it's relatively useful. Now, before we dive into Pascal's principle and what it states and hopefully the meaning behind it, I want to be able to just briefly talk about a couple of items. So first of all, I do want to be able to mention static fluids, because that's what Pascal's principle applies to. So that means these particular fluids, and the word static means that it's not moving. Now, you maybe remember, okay, so for example, things like static friction, okay, you have kind of run into maybe in the past. And if you're talking about pressure and learning about pressure, then you certainly have learned about, for instance, forces. So the word static means that there's no motion. It means it's kind of not dynamic, right, where there is an actual motion. And we are relating it back to fluids, okay? So it's a confined fluid, okay? It's not moving in any way, which typically will mean, so as you can see here, that the net force which is applied to this particular fluid, so it has a net, okay, force of 0. So all the forces kind of cancel themselves off in one particular way. Now, if you are referring to, so this kind of equilibrium point, so if you remember, F net is equal to 0, okay, it is an equilibrium of, let's say, forces. If this actually happens and you're referring to water, well, then very often we're going to be referring to that as hydrostatic, right? So hydro typically just means water, and static means that the actual forces are all canceled off. And again, so that static word comes up in this static fluid concept. So no motion, okay? So everything is kind of confined and you don't have an overall motion, okay, within. So now, if you are jumping into Pascal's principle, well, it does deal with the concept of these enclosed fluids. So now, what do we mean by an enclosed fluid? It means that, it cannot spill out anywhere, right? So it is fully out enclosed, so there's no leakage of any kind. Okay, it is not flowing from one point to another, right? So let's say if you have a hose or something like that, when you're actually opening up, it's not enclosed, it's allowed to actually flow. So we're referring to enclosed fluids in general. Now, what Pascal actually mentioned was the following. So he said something very interesting. He said that if you do apply an additional force, okay, an additional pressure that you have, okay, within these kind of enclosed fluids, and I'll show you what I mean by that, then what happens is that the change in the pressure, so the actual full out change in the pressure, is transmitted, and it is transmitted everywhere within the fluid and the actual walls of the enclosures undiminished. So that change is identical everywhere. So let's see what that means, because this statement, change in pressure is transmitted undiminished, is very powerful. But when you're a student and you're just walking into this, it may be a little bit tricky to be able to understand. So hopefully I can make that a little bit clearer for you. So let's imagine that we have something like this. So we have a container, okay, on top of the container, it's fully enclosed. So as you can see there, so this enclosure, it closes this off, and then there's, it's almost like you have a lid, and then you can, press this down with a certain amount of force, but the liquid inside wouldn't escape. So your particular liquid that you would have, so this, let's say, liquid, is actually, inside of there, okay? And that's what we have. So that liquid is there. So what Pascal is saying is the following, that if you would in any way, okay, press down on this, okay, we typically call these kind of pistons that we might have. So if you start to press down on this, you're going to actually press down, and it's going to have a certain amount of force. So let's say this is the force applied that you would have in here. Now, this force applied that you have is going to be spread over this particular surface area. So you have a surface area, which is this particular lid, and that surface area, so let's call this capital A, that you would result in you actually adding an additional pressure on top of this fluid. So the additional pressure, I'm going to just call this the change in pressure that we would have. Well, that change in pressure that we would have would be nothing else but the force that you apply divided by the area. And this simply just comes from the definition of pressure, right? I can put up a link up above there, back, to the video on just defining pressure in general. Now, once you have this, what Pascal is saying is, now, of course, we have that pressure on top, but because you have the liquid, or the fluid inside, it could be a gas, could be a liquid, could be a plasma. Once you have that fluid inside, that pressure, can actually now be felt everywhere throughout. So anywhere you have it, at any single depth that you have, it will change the overall pressure by the amount, that you have actually applied, on top. So that change on top now is felt at every single point. So it can be felt, somewhere in the middle. It can be felt somewhere, just up above there. It can be all the way at the bottom. So that change in pressure is everywhere. And it also is applied to the actual walls, of the container that this is in. So it's pressing down everywhere. And this is what Pascal has meant, that it is being transmitted undiminished, unchanged. Now, of course, we're assuming that there is no friction, that you might have some losses of some kind. So it is just transferred everywhere from that, so that particular pressure is felt everywhere, and it is equal to the actual pressure right here, the force that you've applied over the surface area of that particular lid. So that's what you would have in here. Now, please don't think that the pressure at every single point is the same. That's not true. This just refers to the change in pressure. So that the change in pressure, is going to be the force applied over the area. Because, of course, as you know, at any depth of a fluid that you have, there is a different pressure. And we're referring to, calculations of pressure near the Earth's surface. So, I did a video on pressure at a particular depth, right? So I can put up a link up above there for you. But as you may recall, now, of course, it depends on what fluid is inside. But if we know what the fluid is, we can figure out what the density is. And then we can also know right away what the pressure at any point is. So if we want to know what the actual height from the top, so let's say if we want to know what the pressure here is, and we're assuming that we're not actually pressing down, let's just assume that nothing is being done, you just have the actual fluid, then that pressure is nothing else but the actual density multiplied by the gravity, and then the actual height. And this, when the height is the height from the top to the bottom. And of course, the deeper that you go, the bigger the pressure is. So the overall pressure that you would have would simply be the actual pressure at a particular depth or a height plus the change in pressure that you have. And this is what Pascal is referring to, that this change in pressure will be felt at every single depth. At the bottom, it will change by delta P, in the middle, on top, does not matter, right? So that's what Pascal's principle is referring to, that it is completely undiminished. And now, what the powerful thing behind this is, and this is where we use this in hydraulic systems, so kind of systems that are enclosed where we do utilize possibly pistons of some kind, to be able to actually lift or uphold extremely heavy weighted objects because of this particular pressure. And where this comes out is from this particular idea, So if you would take, so I'm going to take this, okay, and I kind of shrunk it down, right? So if I have this, and then what I will do is I'm going to connect these together. So let's imagine, okay, what I would do is, so right here, I'm going to erase this, and I'm going to erase this back in here. And let's imagine that I would connect these two together. So, I would take this down, and I'm going to connect this together. And it's exactly the same kind of fluid that I have within both, right? So I'm just kind of connecting it out. And now what I've done, okay, is right here, is I am allowing the actual left-hand side and the right-hand side, so the fluid is enclosed in both. And here, if you press down, as so, right, and you create an actual change in pressure. So let's imagine that this is the pressure number 1 that you would apply. So this is force number 1 that you apply divided by the surface area, and this is the surface area of this, whatever that might be. That gives you the pressure that you would exert. And then what you would find is that the pressure going upwards in here, so would be exactly the same. And that's what, okay, Pascal is allowing us. So his principle is allowing us to do that. Now, what we are making the assumption here is, that we are still exactly at the same height, right? So if the height here is identical, so if that height is identical, we know that on the actual height tops, okay, the pressure is the same if we didn't do anything. But if we pressed down with this P1, so on the left-hand side, so pressure 1, then we would know that pressure number 2, so this pressure that we would have on the opposite side, so pressure number 2, would be equal to the force number 2 divided by the area, okay, number 2 over here, where the area is there. So what this is saying is that pressure 1 would equal to pressure 2 because the pressure change is undiminished throughout. Now, this does not mean that F1 equals to F2 and A1 is equal to A2. In fact, as you can see here, on the left-hand side, it is a much smaller container that contains the actual fluid, and it's a much bigger container on the right-hand side that contains the fluid. It's just that they are interconnected and they're closed in, so the enclosure works, and now we can put in a certain pressure and we'll get the same pressure out. And if someone tells us what those areas are, then we can calculate what the force would be. So this is a very good example of being able to apply Pascal's principle. Now, to end this video, let me just give you kind of a sense what we are referring to. So let's imagine, okay, so for the sake on the left-hand side, because it's a much smaller, and I just want to show you, okay, the power that this actually holds. So let's imagine that on this left-hand side, so right here, we would have, or we would want to be able to calculate our pressure 1. And we would exert a certain amount of force. So we would have a certain amount of force. So let's say that the force maybe, okay, was equal to 5 newtons. And let's imagine that the actual surface area that this was applied over, all right, so over the entire thing, okay, was maybe 10. And, let's say that this was in centimeters squared, all right? Now, of course, it's newtons over centimeters squared. So we would kind of have to change it to meters squared if we wanted to have pascals, but that's not what I'm necessarily interested in here. Now, what I would want to be able to say is, well, let's imagine that I wanted to find my P2, what that pressure is. Well, I do know that that pressure is identical to pressure P1, which would be 5 newtons over 10 centimeters squared. And now, well, this pressure is equal to the force F2, but this, as you can see there, it's a much bigger area. Let's imagine that the area is maybe, 4 times bigger. So maybe this is 40 centimeters squared instead of just 10 centimeters squared. And now what you would find, if the two pressures are identical, so if P1 is equal to P2, then what you would have is you would have 5 newtons divided by the 10 centimeters squared, which would be equal to, and here on the right hand side, this would be 40 centimeters squared. Now they're the same units, and I can find out what that force is. And hold on a second, notice that if you would multiply both sides by the 40, you're going to get 5, okay, multiplied by 40 over 10. And this will tell you, so 10 goes into 44 times, and this would give you 20 newtons of force. So the beauty here is that if you're going to do this, you're capable of actually exerting a much bigger force on the right-hand side than you applied on the left-hand side. And this is how we can uphold, okay, for example, cars, okay, so that we can kind of lift up cars, so they're using exactly this concept, okay, and we can hold them up, and we don't need as much actual force because the pressures are equal. All right, so that's all that I wanted to be able to mention here, and this is not the easiest of topics. I'm also going to do kind of an example or so and do a video on that, but here I just wanted to be able to explain to you what this Pascal's principle is all about, okay? And the key is that I would want you to take out of this is that the pressure is actually transferred. So that is the change in pressure to everywhere within the fluid. And that, okay, is pretty remarkable to be able to see. And it's pressured, okay, which is applied anywhere within the fluid and also on the walls of whatever container it is enclosed in. All right, so that is it. Okay, thanks for watching. We'll see you in a future video. Bye, everybody.